Alright, we're going to be doing problem number 42 of chapter 27 of Physics for Scientists and Engineers, second edition by Knight. The problem that they give us consists of this positively charged rod. It's got length L. We have our superposition particle out here, or a position that we want to reference to. It's at a distance r, specifically from the center line of this rod. So I'm going to add in that, just so we know that this is the center, that's L over 2. Okay. So I'm going to go ahead and start by actually kind of drawing a simplified version of this down here that I can add more stuff to. We'll put in a coordinate system so we know which direction, what variable to use. Let's call it plus y. Plus x. Got our superposition just wherever. And we have our length L. And we have R. Okay, so let's start with our electric field strength formula. That is kind of our universal formula on our list. Electric field strength equals our K constant times charge over R squared times R hat. I'm going to go ahead and talk about R hat right off the bat, get that out of the way. So this is all in line. Since this is in line with the center here, if you imagine a bunch of particles here, there's only going to be one that's just right. It's going to follow the x-axis and contact our superposition point here. Well, we could say that there's like several positive charges on the end here, so hopefully that's still on the camera here. So let's say we got one here and one here. Okay, they all kind of cancel out. Okay, cancels, the y's cancel out, and you end up with just the x. Okay, so really R hat is equal to R hat is equal to R I hat plus 0 J hat all over R, which means that R hat equals just I hat x direction. And so I guess the first thing we'll do is we'll just take a little slice. That's usually how we make these problems work. We have our little slice. We're going to call our slice dx, and its charge at dx is going to be dq. We know that we can express dq as equal to our charge density times our little slice dx. Alright. So obviously there's going to be calculus in this, we all know that. To find the slope of our electric field strength for an undefined position r here, okay, dE is equal to our constant K times dq all over R squared I hat. Okay, well, let's go ahead and replace dq. We don't know what dq is, but we know we can figure out dx because this is all going to be with respect to x here. dE equals K, hopefully this is visible on that camera, K lambda dx all over R squared I hat. I guess we need to figure out what R is. since this r here is not really the r we're talking about for where dx is relative to p, okay, let's look at our maximum distance. Okay, we know the maximum distance from P to the farthest end of the rod is going to be R, this R, plus L over 2, right? Remember we have L over 2, and if we follow this coordinate system as x travels here, depending on dx's location, it's going to be the maximum distance minus where it is relative to the origin here. So we're going to say minus x. Alright, so we can replace this r with this expression here. dE is equal to k lambda dx, let's throw I hat up there, all over r plus L over 2 minus x. And we're going to square that. So this is the dE version. We need the E version, so obviously we need to integrate. At this point I think we can. And then I'll talk about limits and things like that. Let's do it over here. E equals, if we use this, we can take some of these things and move them out front. They're just things, constants in there that we're going to multiply. K, lambda, those are going to come out front, and actually the I hat too, what the heck. K, lambda, I hat times the dancing worm of dx over r plus L over 2 minus x squared. Not to panic, this isn't nearly as bad as it looks. These are just constants. So if, let's say you have a constant in some parenthesized expression with an x in there, okay, when you go ahead and take the derivative of that, all the constants go away. There's no x attached to them. The only thing that would matter is this x. And also we need to keep in mind that we can rewrite this to be a little more user-friendly. E equals k lambda I hat times the integral of r plus L over 2 minus x to the negative 2. Remember, we can do it with our exponents, dx. You could do a u substitution. I'm going to be honest, my teacher actually really hated, my calculus teacher really hated u substitution, and I just kind of evaluate integrals in the method he taught, where you can kind of predict what it took to get where you're at. Just kind of, you know, do a little bit of thought, a little bit of thinking here. So the antiderivative of this expression to the negative 2 power would have been this expression to the negative 1 power. And then you would also need to take care of anything that would happen when you found the derivative of anything inside this expression. Let me go ahead and write that first, since we know that's going to be in it. E equals k lambda I hat. We're integrating here, so let's keep that separate. R plus L over 2 minus x to the negative 1. Alright, now to go from negative 1 here to negative 2, there would have had to have been a negative 1 that came out when we took the derivative. So to counter that, this isn't negative up here. We're going to put a negative 1 value out here, so this negative 1 times that negative 1. Alright. And then also this negative x here we got to take care of. Okay, you find the derivative of the outside, then the inside, all this would have just ended up being negative 1, because x would go to 1, and you have a negative in front of it, so there would be a negative 1 to take care of that. So really these cancel out. We don't need them. Okay.